The definition. So the thermal runaway definition, it's really the exothermic reaction and that it's uncontrolled and becomes unstoppable, and then basically the release of all the energy. So it is meaning that the release of the energy can be in the form of the heat, and then of the gas, so the gas that it's evacuated, and then also particles. So this would be the three major, how the energy is released. And overall, a lot of people say, when we see fire, it's thermal runaway. Well, to be fair, fire is a consequence of the thermal runaway, because when you have it, for example, in the inert environment, you will see at the beginning deflagration, and then you will just see basically a lot of venting. So venting, sparks meaning because of the hot particles ejected outside. These are usually like pieces of the current collectors and the active material, which are heated up, to extensive temperature. So this means over, for example, 300 degrees. And this is at the end. So when the cell vents, at the beginning, you have just a big venting event. Then you have a deflagration, so of the combustible mixture, and then you have just the venting, because then the atmosphere has consumed all available oxygen, and then you have only the inert atmosphere, which is mainly so depending on the chemistry, it's then composed of just few elements.
So you said depending on the chemistry. So do all chemistries suffer from thermal runaway? Or there are like some chemistry that are safer than others?
So I don't really always like to use the expression safer, because every cell can experience exothermic event in a form of thermal runaway. Some of them more severe, some of them less severe. So for me, it's only the matter of definition how severe it will be. So the severity of the case, and then everything what comes with it. So you can also have a very not so significant event. So just a lot of venting. It is duration of the 1 minute. But in this venting, you can have the gases that are released are extremely then can be toxic, which is then causing much more harm than, for example, the other event, which looks horrible. It looks very exothermic, a lot of sparks, a lot of aggressive venting. The amount of heat release, it's beyond what was the other one. But at the end, you just have 90% of the gas release. It is only, for example, three molecules, and that's it. And on the other hand side, you can have, completely toxicity, which is at the end causing a lot more harm. But, it's always the matter of perception. Where does it happen? How it happens? And this is for me how I would answer which chemistry it's, let's just say, how the chemistries are differently reacting.
Okay, so maybe we can change the question and say, what are the less dangerous chemistries?
Again, so for me, it's very funny. I will never say it to you like less dangerous. It depending on, you can have a completely less, so the chemistry that it's not reacting super severe, you can have it in a poor system that it will make it be completely severe. I can make an example of it. The most typical example would be an LFP cell. An LFP cell, it's globally labeled as a safe chemistry. But LFP cell can be also extremely toxic. It can be surprising in a way of how it will react. From my experience, we had, for example, the cells where they had an LFP inside, and then we were triggering them to go into the thermal runaway. And when we triggered the LFP with a certain amount, how you initiate the thermal runaway, it was more severe than an NMC cell. Even though the NMC was 811, the LFP was very, very much severe because it depended. So how we triggered it, it actually at the end was a bit more severe in the effect of it. And also the system overall. So the system design, it is very much depending how the cell will react. So when you have, for example, very cramped space and you put batteries inside, And when the battery goes into the thermal runaway, because you have, for example, either no venting path or just a small amount, you will have a lot of heat transfer to the neighboring cells, and then also gas accumulates, which is then making a very explosive limits can be quickly reached. Then you have, of course, the particle, which can act as an igniter. At the beginning, you have, of course, oxygen present. So you have a deflagration and the whole thing basically explodes. And then you will have a fire and everything because you will be having so much heat just released, and then you have a very high heat transfers. So even though you have an LFP cell, the way how you position it in the system, it matters. And how you operate, it matters. Because with all of these things, you can at the end prevent the worst case scenario of the whole thing, for example, going into complete bust. But yeah, this is usually how I always say it's the cell chemistry defines you a boundary conditions for your system, how you build then around it.
So we can say that this is the root cause of a thermal runaway. So basically the design of the cell.
Not. It can be, of course, the design of the cell. So the root causes are very much, you have a different one. So you can have a root cause can be also how you operate it. So how you're operating the batteries, so operational patterns. Then the root cause can be, of course, the design system. What do you have as a detection method? How do you control after the event is triggered? How do you control it? What are your mitigation strategies if they are really scaled to the boundaries that the cell gives you? So you have a lot of them, and every time you have to go through the whole bunch of lists because they are a bit different, from application to application.
And is there like a problem in which you think the industry is usually, or like everybody's focusing on, but it's not like the most dangerous thing? And then is there something else that you think, or you work every time on with the industry to try to make them understand that they should focus on something else to prevent the thermal runaway?
I do have. It's actually, so I think I made also a post about this. And it is about actually the things that get most attention and the things that don't get a lot of attention. And this is specifically how you also said at the beginning, fire, explosion. These get so much attention, my God. But a lot of things what also doesn't get attention is what type of a venting it is, cold degassing, if you have, for example, particle ejector or not, how the venting path, the venting strategy, it's really built. Is it built really to have only surviving one cell going off, or it can survive like multiple cells going off? Because sometimes it is designed, that one cell can go off and everything is fine, but if two simultaneously go off, it is completely like overkill, and it will be basically the strategy that it will be in place, it will not be suitable. And short circuiting gets a lot of attention, but at the same time, it is maybe getting attention from me on a too much high level. It should be also short circuiting going already, so specifically then preventing electrical arc formation. It should be already addressed on the cell, so really cell to cell connection, and then building it from there. And for me, it's really basically one thing that it's quite hidden are particles and the gas. And here the gas, it's not meaning just in a terms if it happens with the thermal runaway, but also cold degassing. For example, already decommissioned cells, they are degassing because it is the decomposition it's happening inside of the cell. And this part sometimes is just slipping the mind when you're, designing the system that you can have also cold degassing, swelling of these cells. And at the end, this is also then impacting the lifetime. So all of these parts are at the end forming, one big picture. But yeah, with the thermal runaway, the most thing gets fire. And I think it is the common misconception that thermal runaway, it's fire. It's a consequence of the thermal runaway.
You said before that one of the main causes of thermal runaway can also be how you use the battery. So I guess the BMS, the battery management system, plays a huge role in this. Does
Yes.
it? Or okay.
Yeah. Of course, it does play. Especially, it plays it also in the detection. So, okay, it has several roles. So first of all, battery management system also plays it in a way of how you're operating it. So you would like also to have your battery system should have also a good thermal management system in order to really accommodate all the ups and lows of the usage and also of the environmental impact. So in order to maintain the optimal temperature for the cell to not degrade, and also to make sure that when you're cycling, for example, at the higher C rates, that you maintain the cooling as efficient enough as possible, that you have really this heat transfer, so high heat transfer from the cells in order to not cause, for example, a rapid degradation, and with this shortening the lifetime span. And also with the degradation, then you're basically building up the gases or, everything decomposition inside of the cell. And these are all the points that should be taken care of during the operation. Then the BMS, it's extremely important when you would like to detect the thermal runaway or faulty cells, especially when it comes to, for example, detecting a thermal runaway. It is always critical what is your detection strategy, because this is then coupled with the BMS, and how are you sampling the data, so data acquisition, because it doesn't help you if you're sampling every 10 minutes when for example, you have it in idle state, that if it is sampling every 10 minutes, just for the precaution, well, the thermal runaway, if it is happening, it's usually happening quite fast. If it is already past the onset one, it is then happening quite fast, and you should ideally record it in this time. And then also compare, based on the trend at the back, so how you're analyzing the data, compare it, if it is something has happened. So and then of course also what is the next steps after the possibility of the thermal runaway is detected, what are then the next steps that the system must take? Activate cooling, open up certain flaps for the venting strategy. All of these steps needs to be then executed afterwards.
How do you test all of these things? Because I guess it's not very simple to do. Like you don't just put the BMS and then kind of hope something will go wrong and it will detect. Like, what do you do in the lab? Like, do you just take a knife and just puncture, or
Almost, yeah.
you heat it up?
Yeah, almost. So you have a certain way. So for the safety overall, you have to ideally test it from the cell up to the system. And when you test it on the system level, it needs to be with the BMS running in the normal operational mode. This means you shouldn't have any other quasi or the pseudo interactions. It should be really running as an operating, because with this you can at the end really see if it is detecting the thermal runaway and then thermal propagation event or not. With this, how you're training also on the BMS side, so you have so nowadays it's a lot of also ML, so machine learning, and basically the AI comes into the play to really bring the BMS towards the speed that it will be able, based on the voltage, current, temperature, the data, that it's recording, that it's able to then quickly determine if this is going towards for example, thermal runaway or not, because you already have the data from previous tests when you executed the thermal runaway, how the BMS was basically behaving, and these are the topics then you're inserting in your code in order to make your system more agile and faster responding.
Is there a mistake that you see the researchers are making not just about the BMS, but like in general. I don't know, maybe they're focusing on a type of test. Why
Yeah.
they should make like or like, is there like something else that you usually suggest?
So for me, usually with the BMS I wouldn't call it really a mistake. It is just, usually it's connected to the costs about which signals get basically followed, so that you're following, acquiring. And usually you have it like voltage, temperature, delta temperature. You should also combine it also with additional parts, especially when it comes to the safety. You should combine it also with sensors for the gases, for the pressure increase. All of this should be then additionally combined. So for me, it is just here, I wouldn't say a mistake. It is just how good you would like that your system is, how accurate, in order to also avoid false positives. And of course also false negatives. So you should also not just have a traditional way of how your data is acquired, you should also have additional sensors placed in order that you can really confirm that this is a thermal runaway event or not.
And where is the research focusing right now to prevent the thermal runaway?
To really prevent that. So with the prevention of the thermal runaway, they're focused on the separators, on the coating. So this is really on the cell level. Because when you say prevent it, it means that it is not so easy to trigger the thermal runaway. Because at the end of the day, there are active systems, and it is a chemistry which, if you invoke it correctly, you will have an exothermic reaction. It's just how it is, as from the activation parts. So basically what you're trying to do is move these activation layers higher so that it will be not so easy achievable and then also easy triggered. Idea is, so with the coating, with the separators, this is from the lithium ion state. Then you also move to the sodium ion. Common mistakes with the German-speaking people.
Yeah.
With the sodium ion, and then also solid state, or at least semi-solid state batteries, you go into a different part. But at the same time, also there, a thermal runaway, it's possible. So how you're really doing it is with the additives, with type of basically additions that you're putting into your battery, and with the coatings that you have, you're basically moving the bar higher, if this makes sense.
Yes. You just mentioned the solid state batteries, and in the latest year, there is a lot of interest around them.
Yeah.
And one of the main pros that everybody talks about is that you don't have like a short circuit, like you don't have like a thermal runaway. Is it true? Or you can still have, because you said like semi-solid can have a thermal runaway. Also, like, what is a semi-solid? How is it different from a solid state? And which one is safer? And if you can have a thermal runaway in both?
So, bottom line, you can have a thermal runaway in both. You can have a thermal runaway also in the LTO chemistry. So it is something, it is not very common, and how it is triggered, it is extremely difficult, and also the amount of gas release, the temperature that you see, you will not then see, for example, like you see in NMC, so high nickel content NMC cells, you see the temperature that can go over 900 degrees on the surface, so on the solid part, and then you also see on the gas it can go over 1300 degrees. So these are NMC cells. Then you can have an LTO. Everybody now will say, LTO is actually not experiencing the thermal runaway. Well, fun fact, if it is provoked a certain way, it can. But the temperature, how it is behaving, it's then completely different. So these I have a bit of internal, I have seen the LTO go into the thermal runaway, and it's different, it's not so severe, but it's still let's just say, it's still burned. It still emitted a lot of gases. So also think of it when we are testing solid state. We shouldn't think of it from the lithium ion perspective, how we test lithium ion. We should then change the testing methodology because the onset temperatures are higher. And most of our equipment, it's actually like it has, a threshold point, like they're a bit above 200 degrees. And for the solid state, they are much, much higher. And this is then also meaning that the testing methodology needs to change, needs to be a bit different, you need to basically think of it, how can I destroy a cell? I need to destroy a cell. And this is how I also work. It's not also always like, how can I make it safe? How can I destroy it as effective as I can, like as fast as possible? And this is then unlocking so many doors because I look from it, from this perspective, how can I destroy this cell as fast as I can and as quickly as I can? And with this, I will be able to really get the idea, what are then the boundaries? What is the worst case scenario? And this is where it helps me to then also design the system around it, to think of it, how the concept should look like and how the testing should look like to really exploit the cell weaknesses.
So, like, do you think this is actually where the researchers should more focus, like in the question? So you say, like, how can I destroy it quickly? And like, what is instead the usual question researchers ask them?
Normally, how can it be safe? How can there be no thermal runaway? Of course, this is a really good question. It's the most difficult one to answer. But always also think of it, how can I destroy it? Because there is always a way how you can destroy something. That's also, for me, it's always this thinking, you have a perfect system. Let's exploit all of its weaknesses. Because everything also, when you're designing the perfect concept, it's amazing. You should also think about all the weaknesses that come with it and be self-critical how you're doing. Of course, it's your baby. When you're designing your system, either from the BESS, automotive, whichever application, it's your baby. Think of it, all the things that could go wrong. And then think if you're really designed for this way. And then also think at how you can destroy it. And with this, it will be at the end also, how to say, back testing also yourself. How did you do?
That's super interesting. I never thought about it like, I mean, I think it makes it actually cooler to think, how can I destroy this? Like, I would wake up every day so excited.
Yeah.
Like, yes, how can I destroy it like even faster?
Yeah, literally, I'm sorry for this, but this was literally when I was running my task forces and everything. So I had 5 task forces all at once, and I loved it. I loved everything because I always, when I stepped into the room, I was like, let's destroy it. Destroy it completely. Let's take it apart. Let's destroy it. I'll just take it apart. Let's destroy it apart. And this was like, everybody was like, no. I was like, yes. Let's see how much it can have, because at the end, when the customers come to you, they always come to you with the idea, let's make it safe. And then I said, what do you mean by that? Do you mean that you really want to make it safe, or would you like to pass the standard? And then this sub question, they're like, we would like to make it safe. I said, okay. This means if you would like to make it safe, we will destroy it completely, we would exploit it. And this is then also driving a lot of costs. And then a lot of times happens that then they were like, okay, we just want to pass the standard because this is really time consuming and also resources consuming. Of course, now it is, you have a lot of lessons learned, so you can do it faster, of course. But at the end of the day, most of the people want to pass the standards because the standards, they give you a certain certification, a certain point of standing. But at the end of the day, it's always a question, is it really safe? Or it is just, passing the standard?
Yeah, indeed. And I'm sure you also heard about the battery passport they're making now.
Yes.
And do you know something like more about? I'm 100% sure there's gonna be like the thermal runaway legislation about something. Can you tell us a bit more about what this battery passport is gonna tell about battery safety?
I think the idea or all of the batteries passport, it's very nice. So for the traceability and all of this stuff, I'm just a bit afraid that at the end it will turn into a lot of bureaucracy, which will
Yeah.
not be ideal. And also one point is when we are talking about the thermal runaway, we can talk about the thermal runaway of a single cell. If there will be also inside the thermal propagation part, so this when you have it, multiple cells together, it's very hard to quantify it because so the system will behave completely different. I will break it down. Like when the cell, you have a thermal runaway, and if you put it under a different conditions, it will behave differently in all these conditions, one single cell. So if it will be inside, of course, I believe that there will be a certain what are also right now, which standards the battery needs to pass in order to be labeled, to pass all the safety criteria. But this doesn't necessarily mean that it is, like no thermal runaway will happen, because these type of cells are not tested then when they are aged. Of course, this, then the performance is different. And now think of it, okay, this is just the cell we are not talking. But about when you put the cell into the system, it's behaving completely different because, as I said already earlier, you have a lot of, so the system boundaries are basically defining the safety of overall. So, for me, it's then always this, how would this be then, how would this be assessed? Only on the fresh cell? How will this be assessed, when the cell gets cycled? Who will test this? Because the thing is then, depending, how I said, on how you use it, which type of environmental impact were they, mechanical, electrical, all of these impactors, they are then defining how your system will be behaving. So it's very hard to, I would say it's for me very hard to quantify it in a way that it would be suitable for the battery passport. Of course, you can put in a thermal runaway test, but then you should also put the methodology, how you do it, like very much public, and then make everyone test it according to these methodologies, because you can test a cell in a million ways and you will also get a million results. Always depends what is the goal of your test. As you know, as a scientist, you know that when your idea of making a test, you always need to think about what will be the goal. What do I want to achieve with this? And then the methodology is according to that goal. This is also something that it should be done also for the batteries.
Yeah, indeed. I think the idea is very, very interesting. I like it a lot. But we need to see how the execution is gonna go.
Yeah.
Especially because I think it would be best to make third companies test the batteries for this and not leave it to their own company, because like you can still fake or hide some data in order to keep selling.
Not really fake. I think they are really transparent with this. You can just adjust the boundaries. What type of a nail you use, everything of this, you can just adjust it and the result will be according to the boundaries. I agree with you. So I think it should be like that there should be a uniform methodology, a really methodology how it should be done. And ideally, it's tested by the third parties. So not by in-house testing, but the third parties, which they will have the agenda to destroy the cell. And if you have this type of agenda to really destroy the cell, to really test it, then I believe that you will also, as a consumer, more believe into the results that you will be given.
Yeah.
But as I said, this can be only done, for example, on the thermal runaway. Immediately when we go into the thermal propagation, it becomes a bit more fluffed. When you have your system, when you're testing for the thermal propagation, it will be always dependent on the, how you test it for the propagation side, because the system will actually set, you will get a bit more information how the system is behaving. I don't know if really this makes sense, but yeah.
Yeah, I think your idea of destroying not just the cell, but perhaps also the whole pack would be extremely useful, because then you know when the multiple packs, of course, like if you just test one, is like useless. But then you will know what are the limits of that pack, because it's not just about the cell, it's about also the design, as you said, and how you use it, etc. So in different things. So
Yeah.
I don't know how the European Union is is doing it, is gonna do this, but I really hope they're gonna get some people on board like you to define the process on how to test and what to have in order to have this passport.
I mean, I would love to be there to also, discuss this. It is just to know, currently there are standards, like Chinese standards. For me, in my opinion, they are, for me, most advanced in the terms of the battery safety, especially on the EV side. And then, of course, you have it on the UL side. They are also advanced into the BESS testing. But again, in these standards, for me, they are presenting a base, a bare minimum. You should also exceed that thing. And also within the standard, because how you're reading it, there is a room of interpretation. How you trigger, which is the cell that you pick for triggering. Because if it is just saying, that it should be in the central of the system, great. What about if your weak point is actually at the corner of the system? And this thing, if you trigger it there, it will just blow up the whole thing. You have so much room for interpretation. I would prefer that it is like identify the most critical parts, like the most awful locations in the system, and then test those. Of course, some of them might disagree that it should be in the center, yes, but also test the ones that are identified as the most critical ones, and then test those. And also you have to argument, why do you think those ones are the most critical? Idea is always to go with someone who is not really, within the company, that you have like a third person who does this, because his goal will not be pushing the product on the market, but it would be really idea of let's have a safe product on the market.
Yeah, indeed, totally agree. Is there something like you want to add? Because I finished all my questions, but is there something that you think we didn't cover, and like, I don't know, advices or something else that you would like to tell the audience?
So what I would like to tell the audience is that when they see the thermal runaway and everything, maybe one thing is don't always go and put something over it or something like this. Please remove, especially because of a lot of fires happening in the micromobility. And this is something that it's currently also what I'm working with. It's extremely difficult. Of course, it's in your home, you would like to attend, but a lot of times has happened that then it backfired to the person who wanted to put it out, and then they went into the coma, they got poisoned. So this would be also one part. I would like that also the safety translates into how we handle with the batteries in case something has happened, and also that mobility, so micromobility, all these home storage systems, that they also get under the safety regulations, because currently they are not. And this is like my idea, the final message, what I would like to see. It's also more attention to the details on this side.
Amazing. So Neza, thank you so much
Welcome.
for this interview. It was super interesting. I'm gonna leave as like your contacts, and if you allow me, also I can put your emails. So if anybody's interested, they can contact you directly through email.
Yeah, of course. Thank you very much for having me.
Yeah, of course. And we see each other on LinkedIn.
You see us on LinkedIn. Ciao.